So in this lecture, we're going to try to use all those equations that we introduced for simple harmonic motion. So you can see here I've got all the equations in the box over there on the right hand side, and there's a whole bunch of equations. And so what we're going to do is we're going to take a mass on a spring oscillating according to the equation that x is equal to 0.450 times the cosine of 6.40 times t, where x is in meters and t is in seconds. We're told that it's a 0.600 kilogram mass, and based on just the equation and the mass, we're going to find the amplitude, the angular frequency omega, and the linear frequency f, the period, the spring constant, the total energy, the maximum speed, the maximum acceleration, and then we'll find the speed and the energies at when it's displaced by a distance of 0.30 meters. So let's jump in. So let's start off with the first thing. What's the amplitude? Well, our equation is that x is equal to 0.45 cosine 6.40 t. And remember, our equation is x is equal to a cosine omega t. So if I compare the two equations, you can see that I've got 0.45 in front, so that must be my amplitude A. So the amplitude is just 0.45 meters. It's the number in front of the cosine function. So the next one, we want to know what's the angular frequency. Well, again, if I look at that equation, the equation is cosine omega t. So the number that's in front of the t must be the angular frequency omega. So omega is going to be 6.40 just from reading the equation for x. And the linear frequency is just omega over 2 pi. So I divide 6.40 by 2 pi, and I get 1.019 hertz. Okay, so A and B were pretty easy just based on reading the equation. What's the period? Well, the period, remember from talking about circular motion back in Module 5, period is 1 over the frequency. So it's 1 over 1.019 or 0.98 seconds. So all of this so far has pretty much just been based on definitions. All right, let's continue on to part D. All right, so in part D, we want to find the spring constant. In E, we want to find the maximum speed. In F, we want to find the total energy. And in G, we want to find the maximum acceleration. So how can I find the spring constant? Well, if you look at the equations, I could use omega is root k over m because I know my omega is 6.40. I know my m is 0.60. So I would just rearrange that to give me the spring constant. So how do I rearrange it? First thing I would do is get rid of the square root. So I would square both sides and get omega squared is k over m. So that means that k is equal to m times omega squared. And then I just put in my numbers, and I get 24.576 newtons per meter, or about 25 newtons per meter. All right, part E, what's the maximum speed? Well, maximum speed is a times omega, or a times root k over m. And in the problem, we're basically given a and we're given omega, so I would use that part. So a times omega, 0.45 times 6.40, which gives me 2.88 meters per second. F, what's the total energy? Well, the total energy, we had two equations. That's 1/2 Ka squared or 1/2 mv max squared. I could use either part. I could use 1/2 Ka squared or 1/2 mv max squared, because now we have all of those things. We have K, we have A, we have M, and we have V max. Excuse me. And if you calculate it either way, you'll get the same answer of 2.488 joules, or about, excuse me, 2.5 joules. What's the maximum acceleration? Maximum acceleration is a times omega squared, or k times a over m. So if I put in a times omega squared, and the only reason I chose to do that is because a and omega were given in the problem, so I didn't have to rely on a number I'd calculated. 0.45 times 6.40 squared is 18.4 meters per second squared. Okay, so what else do we have? Well, we're going to look at what happens when we're at a position of 0.30 meters. So remember, looking at the equation, our amplitude is 45 centimeters. And so we're going to be going about 2/3 of the way out to 30 centimeters. We want to find out what's the speed there, and what's the kinetic energy, and what's the potential energy there. Okay, so first of all, we'll find the speed there, and we have only one equation we can use. That's the speed as a function of x is v max times the square root of 1 minus x squared over a squared. So v max we figured out was 2.88. And then I put in the square root 1 minus 0.30 squared over 0.45 squared. So I get 2.147, or about 2.2 meters per second. So now I know my V at x equals 30 centimeters. I can find my kinetic energy. So kinetic energy is 1/2 mv squared. So it's 1/2 times 0.6 kilograms times that 2.147. I use the unrounded number instead of the rounded number. It gives me 1.3824, about 1.4 joules. The potential energy is 1/2 kx squared. My x is my 0.3 meters, and my k I found in an earlier part. So if I put that in, I get 1.106, or about 1.1 joules. And if I check here, if I add up the total energy, E total is 1.4 plus 1.1, or 2.5 joules. And if we go back to the previous slide, you can see I figured out that the total energy was 2.5 joules. So we get agreement there. Okay, so alternatively, I could also have done that the potential energy was the total energy minus the kinetic energy. And again, there's so many equations here that there's multiple ways in which I can figure out, multiple orders in which I can figure out the things. So your problem is going to be to use all of those equations, which I've summarized here at the bottom, to figure out the total energy, the spring constant, the angular and linear frequency, so that's omega and f, the maximum acceleration, and then write the equation for x of t. So x is equal to a cosine omega t. So once you know your a and your omega, you're going to put it in and give an equation for x like we had for the previous problem. And remember, the mass is given in grams. You need to convert that into kilograms to get the correct answer.